Hi, welcome to the Unit 1.2C video, Foundations of Chemistry. This is the last video in this series where we examine different representations of matter. So we're focusing on the second half of the first key question. In this video, you be sure you annotate just like with every other video note packet combo. All right, what we've been doing in these series of lessons is looking at the six basic representations of matter, and we've covered almost all of them now except for particle diagrams. So what are particle diagrams? First of all, particle diagrams are super helpful. I can't emphasize that enough. Particle diagrams are super helpful. A lot of times when you are confused about something, if you take especially if it involves matter, if you take the time to draw out a particle diagram, it may help you see and understand things. So with that being said, what are they? Particle diagrams are simple. We just utilize spheres to represent all forms of matter, whether it's atoms, ions, molecules, parts of a molecule, doesn't matter. And you can choose to label them or not label them. And again, we use them to explain properties and also keep track of atoms and particles during any change or process. So we're going to look at examples here of how we utilize particle diagrams. The first one is particle diagrams are useful in explaining characteristics of solids, liquids, and gases, the three major phases of pure substances. So for your first CFU, since you've seen this before, my question to you is, how do the particle diagrams explain the characteristics of solid, liquid, and gas? And those characteristics are listed below each phase. So you're going to pause the video now, and then when you're ready to check your answer, press play. All right, so particles are extremely close in, of a solid are extremely close and orderly. So you can see that here it looks very ordered and they're really close together. And so that helps to explain the fact that the solid is rigid, it has a fixed shape and a fixed volume. You cannot squash this because they don't really have much room to move, okay? For a liquid, on the other hand, the particles are close, but they're randomly arranged. So that says that they're not rigid. That's why liquids can float, because they're like sort of random, like there's a little bit of room there. But there's not a lot of room that you can really squash or compress a liquid as well. Because they are randomly arranged, they do not have a fixed shape. So they take the shape of the container. Gases, on the other hand, they're randomly arranged and they're really far apart, so they will take up the entire volume or space of the container. They also don't have a fixed shape because they're so far apart, and they're not rigid. So of the three phases, this is the most compressible phase. Okay, the next way that we can use particle diagrams is to explain bonds and characteristics of different types of pure substances. Remember, many characteristics of pure substances can be explained by the atoms and the bonds within the pure substance. So we're going to start with looking at metallic bonds. Metallic bonds are described as the nucleus of a metal and its core or inner electrons. So that's what's shown here in yellow, are floating in a sea of its valence electrons. That's what's shown here in green. So the valence electrons are just sort of like floating around, and they're not attached to one particular atom. And so the nucleus, along with the core electrons, can sort of float around in this sea of electrons. The second type of bond we look at is ionic. So remember, ionic is made of a cation and an anion. Cations have positive charge, anions are negatively charged, and that's what's shown here. The key thing when showing ionic bonding is that opposites attract. So what you should find around a positive charge are negative ions, and what you should find around a negative charge are positive ions. You shouldn't see two negatives near each other. So they have what's called like a lattice or network of positive and negative charges. The next one is an alloy. Alloys are made mostly of metal, but there's something else mixed in. So it's not a pure substance, actually. It's a mixture, a homogeneous mixture, because it looks the same. With that being said, the things that are mixed into an alloy can be other metals, or sometimes they can be nonmetals. For example, steel is an alloy of iron and carbon. So the way that alloys are usually drawn, you have the metals, which are usually shown as the bigger or larger atoms, because metals are usually larger. And then mixed in there, if especially particularly if it's a non-metal, you have these smaller, a few smaller of the mix-ins. And this is sort of randomly, usually shown randomly arranged, but that's what an alloy looks like. Last one, network covalent. So network covalent, again, that word network meaning like a lattice or what have you. Here we have shown an example of diamond and graphite, and you can see they're these atoms connected by these bonds here that are just sort of arranged in this network. They're all kind of connected some way. And so network covalents are typically they're brittle. Things like diamond can be hard, but they have a varying characteristics. Graphite, for example, is what, I don't know if they still use it, but they would use it to make pencil lead. Okay, so now let's talk about some properties that we can explain. And the two we're going to look at here are metals, the properties of metal being malleable, and ionic compounds being brittle. So I'm going to press this play on this video here. So this is metallic bonding. You have the nuclei, and then these little green things are the sea of electrons. Now, when you hit a metal, it's going to bend. It's not going to break. Well, why is that? That's because when you hit a metal, the metal sort of can shift inside the sea of electrons, and since the nucleus, along with its core electrons, that part is positively charged because you have the nucleus and you don't have quite enough electrons from the core to balance out the charge of the protons in the nucleus. So the nucleus and the core are positively charged. That's shown with a 3+ charge here, and those valence electrons it's floating around. So when you hit it, the positive parts don't hook up with another positive part. They're still surrounded by these negative valence electrons, and that's what allows it to like bend and break, right? I'm sorry, not break, but to bend and be malleable. On the other hand, with an ionic compound, so like a salt, if you were to hit something like that, it's brittle. Why? Because what happens if you hit it, then as you can see here, 2 positives and 2 negatives will line up, and they don't want that. So they're going to shatter once that happens, you know? So that's the reason why ionic compounds are brittle. Okay, so for your next CFU, you're going to draw a particle diagram for potassium nitrate, and you need to show it with at least 12 particles. So you need to see at least 12 particles. When you are, or circles. When you are ready, press play and the answer will be revealed. Okay, so here is the answer, particle diagram for potassium nitrate. It's the main thing to know is that potassium nitrate is an ionic compound, so you should draw particles with positive and negative charges on them, and they need to be labeled for ionic compounds. And you want to make sure that there are no 2 positive charges or no 2 negative charges touching. Now we're going to move into our using particle diagrams to explain what happens during a chemical or physical change. So we're going to start with physical changes, but you've also seen this before back in the first video where you were asked to draw the particle diagram for the sublimation of dry ice or CO2. And so you did use a particle diagram to show a physical change. A physical change being something that when it occurs, the matter itself does not change. You just change like the state it's in, for example. What we're going to look at here is the physical change that occurs when we dissolve a salt, an ionic compound, in water. That's known as dissolution. When it's dissolving a salt, you can also use the word ionization because you're breaking the salt down into its ions. So those are words I might want to write down: dissolution and ionization. Okay, first of all, why does it happen? Remember that a water molecule is polar, so it has a positive and negative sides, and that's indicated here. These are lowercase deltas, by the way, the Greek letter delta, so it's lowercase delta. They use that to represent partial negative and partial positive charges of a polar molecule. And when water comes in contact with an ionic compound, it can break the ionic compound apart, and the negative side of the water molecule, which is where the oxygens are going to surround the positive cation of the salt, And the positive side of the water molecule, which is where the hydrogens are going to surround the negative anion of the salt. And so the thing to always keep in the back of your mind that opposites attract here, and so that's the reason why the water sort of arranges itself around the salt in that way. And here there's just these two like GIFs or GIFs, whatever they're called, that sort of just show that process if you would like to have an extra visual. I particularly like this one because they kind of like fade off and disappear in the background, which is kind of what you envision to happen when you take a clump of salt and you dissolve it in water and all of a sudden you don't see it anymore. Okay, so now your job here is to draw the particle diagram for the dissolution of potassium nitrate in water. And you want to be sure to use at least 8 water molecules. One clue here for the polyatomic ions, instead of drawing out all of the atoms, like the nitrogen and the 3 oxygens around it, the easiest thing to do is just draw the nitrate as in a circle. So just because it's grouped together, so just have one circle for it. All right, when you're ready to check your answer, press play and the answer will be revealed. Okay, so you should have something like this. The main thing is that the oxygens of the water, which are shown here in orange, are surrounding the positive cation, and the hydrogens of the water, which is shown here in green, are surrounding the negative anion. Last example we're going to look at is the particle diagrams for a chemical change. And here we have the decomposition of magnesium carbonate, which breaks down to magnesium oxide and carbon dioxide. And so we can show this this process. This is a chemical reaction with particle diagrams. And the cool thing is it helps us to keep track of the atoms and make sure that it's actually balanced. So we have 1 magnesium this side, we have 1 on that side. 1 carbon, 1 carbon. 3 oxygens, 3 oxygens. So it's super helpful for that. It's also helpful for understanding what this process is, so we can see that we are breaking this down. We're decomposing magnesium carbonate into these 2 separate things. All right, so for your last CFU, you're going to draw the particle diagram for the double displacement reaction shown below. Now, double displacement is a type of chemical reaction. In the next set of videos, we're going to learn about the different types of chemical reactions, so don't worry if you don't know that word now. And you also want to use the particle diagram to prove that this reaction is balanced. So I started you off here. We have ammonium fluoride. I drew the particle diagram for that. And silver nitrate. I drew the particle diagram for that. Your job is to finish this. And again, for the polyatomic ions, you see how I just drew them into a single circle. I would recommend you do that as well. So what would the products look like in their particle diagram form? When you're ready to check your answers, press play and the answer will be revealed. All right, so here is the answer for that CFU, and you can see here it kind of shows like a switching of the cations. The cations sort of just switch places, and you'll notice that for this chemical reaction, it's balanced because you have the same number of particles or atoms on both sides. All right, so we just went through in this series of videos the 6 basic representations. We covered atomic symbols, chemical formulas, Lewis law structures, VSEPR models, and particle diagrams. All of these representations we will be using throughout the year to help us make sense of, understand, and explain chemistry. I hope you found this video helpful. Have a quality day.